Dear students, in today's class, I will draw the energy band diagram of heterojunctions. And I hope you are familiar with the energy band diagram of p-n silicon homojunctions. Anyway, I will very quickly go through that. This is a p-n silicon homojunction. When a p-n junction is formed, there will be the accumulation of charges at the junction. And there will be potential energy variation, that is due to the charge migration. You may be aware of these things. And the variation, it may look like this. So when you draw the energy band diagram, this axis is energy. So at the junction, this plus the potential energy variation, that is towards negative, it will bend like this, and then it continues to the N junction. This is EC, the conduction band energy level, and this one is the valence band energy level EV, and the Fermi level EF. It will be constant steady line. There is probability of finding electrons. It will be very large at the conduction band, that is for N region, and the probability it will be large at valence band, that is for P region. Okay. Suppose this region is N and this side is P. I just reversed it. Here also the migration of charges, the electrons, it will migrate from here to here, and holes will move from here to here. Okay. So the potential energy variation, it will be like this. It is get reversed. Okay. So the band diagram also vary like this. So in both the cases, the band bending, it will be there, and it is very smooth curve based on the accumulation of charges. Now we can draw the energy band diagram of heterostructures. Let us take an N-type gas and P-type gas, gallium arsenide. We know these are two different semiconductors with different band gaps. Gas is wide band gap material, and gas, it is narrow band gap material. So before joining, it will be like this. Due to the band gap difference, there is energy discontinuity at the junction. And one more thing, and why we are drawing EC here, EC of gallium arsenide here. Why it can be here or here? Because all the energy levels, it will be represented with respect to the vacuum level, vacuum energy level, that is E vacuum. The energy gap between EC and E vacuum, it is much higher than that of aluminum gallium arsenide. Okay. Then at the junction, there is delta EC, that is energy discontinuity between gas and gas, that is for conduction bands, and delta EV for the valence band region. Importantly, the delta EC, discontinuity downwards, and for delta EV, the discontinuity upwards is very important. So when you join the junction, as you know, there will be charge migration, and in NP junction, because of charge migration, there will be potential energy variation, and it will be like this, energy variation. But here you need to be very careful, because in addition to the potential energy variation, there is energy discontinuity. There is delta EC and delta EV. Okay. So when you draw the band diagram, EC from gas, it's bending in this direction. That is because of the potential variation. Then at the junction, there is energy discontinuity, that is delta EC downwards. Okay. Then after discontinuity, towards gallium arsenide, energy bends like this, as the potential is still varying like this. Okay. So this is delta EC. Then in the valence band energy level, that is EV, it is bending like this towards the junction as per the potential energy variation. And at the junction, that is delta EV, that is discontinuity delta EV upwards. After that, it is following the bending as per the potential energy variation like this. Okay. And if there was no energy discontinuity, the band bending, that would have been very, very smooth, just like we have seen in homojunctions. Okay. So because of the energy discontinuity, a potential well is formed at the junction. It is triangular in shape and it is called a triangular potential well. So during the charge migration, the electrons will be trapped inside this well. Here, the electron movement is confined. So it is called two-dimensional electron gas or 2DEG. So here is the energy band diagram of N-type L gas and P-type gas, gallium arsenide. Here I have taken P-type gas. You can also select intrinsic gas instead of P-type gas. Okay. You can also practice by drawing the energy band diagram of P-type L gas and N-type gallium arsenide heterostructures. Anyway, now I am interested in drawing the energy band diagram of a double heterojunction. Now take P-type, P plus type L gas, plus means heavily doped P region, P-type L gas, then P-type gas, gallium arsenide, and N-type L gas. So there are two junctions, two heterojunctions. So before joining the band diagram, it will be like this. Check the Fermi levels. In P plus, it's very, very close to the valence band. When you join, there is P plus and P junction. The charge migration, it will be like a PN junction. Okay. So the potential energy variation, it will be like this. Then here also there is a PN junction and there is potential variation just like this. Then here is energy discontinuity delta EC at these two junctions and delta EV at here and here. So after joining, when you draw the complete band diagram, it will be like this: band bending, then discontinuity downwards, then continuing, then it bends towards junction, then upward discontinuity. After that, it follows the bending. Okay. So in valence band region, the energy level, it will bend like this, then discontinuity upwards, then follows the bending. Here at the junction, there is discontinuity downwards and it follows. Okay. So we have seen the double heterojunction, double heterostructure and its energy band diagram. These double heterojunctions, they are used in producing highly powerful lasers, and we will discuss the working principle in module 6. In the next class, we can discuss about modulation doped heterojunctions. Okay, thank you.